Welcome to the lecture series on numerical methods, finite difference approach. In the last lecture, we have discussed this elliptic equations, that is like classical elliptic equations as Poisson equation and Laplace equation. And we have adopted like a Gauss iteration method to find the solutions. And in Gauss iterated methods, especially we are just going for like several iterations to get this corrected values there. And in the present lecture, we will discuss about this SOR method followed with some of the examples. And if you will just go for this like SOR method here, so specifically if you will just say here the iterative methods for solving linear system of equations, namely like Gauss-Jacobi and Gauss-Seidel method, can be modified to increase their rate of convergence. And these improved methods are known as SOR methods. They are also called sometimes as Leibman's method. And the scheme for solution of Poisson equation by Gauss-Seidel method is discussed in the previous lecture, where we have used like different iterative procedures to obtain the solutions and the different boundary condition treatments there itself. So, if you just use the same Gauss-Seidel method here, so then this equation which is represented in the form of like del square u by del x square plus del square u by del y square, which is written as f of x y. And if we are just denoting this grid points are in the form of like x coordinate as the I grid points and the y coordinates as the j coordinates there. So, then we are just signifying all these grid points are in the form of like here as I is varying in the x axis, which is just denoted as I equals to 0, I equals to 1 to up to I equals to m here, and j is varying from j equals to 0 to j equals to 1 to up to j equals to n here. And especially in each of these coordinate points, if you just write that are in the form of like ij there, so that is why we are just signifying this central difference scheme as in the form of like ui minus 1j minus 2 uij plus ui plus 1j by del x square, plus if you will just go for this discretization here, it can be written in the form of like uij minus 1 minus 2 uij plus uij plus 1 by del y square, this equals to fij, and which in turn can be written in the form of like uij to the power n plus 1, this equals to 1 by 4 ui minus 1j whole to the power n plus 1 plus uij minus 1 n plus 1 ui plus 1j whole power n plus uij plus 1 n minus h square fij. And already in the last lecture I have discussed that why we are just considering this I minus 1 and j minus 1 in the powers of n plus 1 and this I plus 1 and j plus 1 as power of n there itself. Since this values like I minus 1 and j minus 1, it can be computed from this previous steps which can be updated in the next iterated level there, where itself we can just consider I is varying from 1 to m here and like j is varying from 1 to n minus 1. If we will have this boundary condition like a derivative boundary condition along this boundary I equals to like last boundary m there itself. And if you just go for this successive over relaxation scheme for a Gauss-Seidel method for computing the value of uij to the power n plus 1 from this previous equation, which is expressed in the form of equation 14.1 here, that can be written in the form of uij to the power n plus 1, this equals to uij to the power n plus omega rij here, where rij is nothing but if you will just see here, this can be written as like a previous iterated scheme whatever we have just written, that is in the form of uij to the power n plus 1 minus uij to the power n here. So, this means that the value obtained from this Gauss-Seidel iterated method minus value from this previous iteration. So, which can be written as the residual here or rij especially we can just say. And if you will just put this rij value in the first expression here, then we can just write this modified expression as uij to the power n plus 1 as, since ij is present there itself also here. So, that is why uij can be taken common. So, 1 minus omega into uij to the power n plus omega by 4 ui minus 1j to the power n plus 1 uij minus 1 power n plus 1. So, ui plus 1j to the power n here, then uij plus 1 whole to the power n minus h square fij here. And in a combined form, if you just write here, then it can be written as 1 minus omega uij to the power n plus omega into value, if you just see this value which is computed by only this Gauss-Seidel iteration method. So, that is why it is just written value computed by Gauss-Seidel method there itself. And if this condition is not prescribed as the normal derivative condition or the derivative condition along the boundary, so we can just vary these values I from 1 to m minus 1 and j is varying from 1 to n minus 1 there itself. And specifically if the derivative boundary condition if it is there, then we have to vary this value I is from 1 to m there itself. So, how we can just choose this omega value, that specifically depends on some scheme here. So, especially this scheme I have just written it in direct form, since there are some specified theorems for this determination of omega optional values. So, this opted value, if you can just see here that omega opted as like 2 minus 2 square root of 1 minus 4 t square, and which can be obtained from this eigenvalue calculation, especially this t value, and we have just written it in a direct form as t equals to cos of phi by m plus cos of phi by n. And for large m and n, so especially this term will be like varied as here 2 minus square root of 2 pi square root of 1 by m square plus 1 by n square. And if we will just consider this grid spaces or this grid sizes are equal, and this total length is also equal, m equals to n, this total grid sizes. So, then we can just write this one as 2 by m square here. So, 2 by m square means square root 2 by m here. So, square root 2 into 2. So, that is why it is just giving you 2 pi by m, and if I will just take common here 2. So, I can just write 1 minus pi by m here. So, we are just opting here two different conditions, that is a successive under relaxation and successive over relaxation. Sometimes whenever we will just go for this higher computations, so some schemes maybe it will converge within certain ranges, like if omega is mentioned like 0 to 1 there itself, and sometimes we can just find this system will converge when omega is lying between 1 to 2 there itself. And if we are just choosing omega less than 1 here, this scheme is known as under relaxed. And if we will just consider this omega lying between 1 to 2 here, the scheme is said to be over relaxed. So, by iterated manner we can just test and we can just say that whether we can just apply this over relaxation method or the under relaxation method. So, if we will just go for this practical example here that we have just considered for like earlier method, that is Gauss-Seidel method. So, how these values are improved we can just check by considering the same example here also. So, if you will just consider the same example here, that is in the form of del square u by del y x square plus del square u by del y square, this equals to 0.5, which is defined over a rectangular domain, x lies between 0 to 0.6 and y is lying between 0 to 0.6 with boundary conditions u equals to 1 at 3 sides, especially that is x equals to 0, y equals to 0 and y equals to 0.6, and del u by del x equals to u on x equals to 0.6 here by considering h equals to 0.2, and specifically we will just use here SOR method. So, that is why we need a like a relaxation parameter, especially this is just provided as a over relaxation parameter which is given as 1.2 here. And if you will just specify these boundary conditions in the grid domain here, that can be written as since we have just defined at y equals to 0, u is specified as 1 here, and at x equals to 0, this is also specified u equals to 1 here, and at y equals to n, it is just specified as u equals to 1 there, and at the last boundary x equals to like m here, or x equals to, we can just say that the last boundary I equals to 3 here, we will have del u by del x equals to u there. So, that is why we are just considering this cell as the fictitious cell, where these values will be updated from these two values there itself. When this j will vary from 1 to 2 there itself, and I will vary from like 1 to 3 here, since these are these unknown nodes there itself. And if you just go for this like central difference approximation along the last boundary for x equals to 0.6, we can just find this u4j, this equals to u2j plus 0.4 u3j, since from this point we can just say that is as u m plus 1 j minus u m minus 1 j by 2 h. This is defined as in the form of u m j there. So, that is why if you will just keep fixed j there itself and m is considered here as 3. So, that is why we can just write this one as u 3 j, this equals to u 4 j minus u 2 j by 2 h. So, 2 h especially 2 into h is considered as a 0.2 here. So, that is why this will just give you 0.4 and u 4 j especially it can be represented as like u 2 j plus 0.4 into u 3 j, which is this statement here. And if you will just go for the further process here, the successive over relaxation scheme at different points is defined in the form of this total scheme, which is obtained from this like a Gauss-Seidel method, and this will be just computed from this previous type of calculation there. So, that is why uij to the power n plus 1, it can be written as 1 minus omega uij to the power n plus omega by 4 into Gauss-Seidel iterated method value. That is nothing but ui minus 1 j power n plus 1 plus uij minus 1 n plus 1 plus ui plus 1 j n plus uij plus 1 n minus h square fij. So, if you will just put here I equals to 1 and j equals to 1, then we can just write this one as like 1 minus omega, and this is nothing but u11 to the power n here plus omega by 4. So, if I will just put here I equals to 1, then the value will be reduced to like 0 here. If I will put j equals to 1 here, this can be reduced to as 1 there, and I remains same here. So, I equals to 1, then j minus 1, this is nothing but 0 here, then I plus 1, that is 1 plus 1 is 2 here, and j equals to 1, then I equals to 1 here, then j plus 1, 1 plus 1, this is nothing but 2 here. So, minus h square f11 there. If you will just see here, so this 0 1 condition it is known to us, 1 0 condition it is known to us. So, that is why this is has just taken the value as 1 here, this has taken the value as 1 here, and this can be considered as minus 0.02 here. Since f11 it is just prescribed as 0.5 and h is given as 0.2. So, that is why h square equals to, you can just write as multiplication of this f11, which will be nothing but 0.02 here. And if you will just put this 1 minus omega in a compact form here, this means that omega value is also specified here, omega is given as like 1.2. So, 1.2, this means that 1 minus 1.2, you can just write this one as minus 0.2 here, and this is nothing but multiplication of u11 to the power n plus this omega is 1.2 by 4 here. So, that is nothing but 0.3 here, and into this one u21 and u12, and this is the modified value, that is as 1.98 here. And similarly, if you will just go for u21 value keeping fixed j, if you will just see here, j value is fixed there, only I is varying here, I is varying from 1 to 2. So, that is why if you will just consider I equals to 2 and j equals to 1 here, so especially you can just find this 1 minus omega, then this will be u21 n here plus omega by 4, and if I will just put I equals to 2 here, this will just give you like 2 minus 1, that is nothing but 1 here, j is 1, then I is 2 here, then j minus 1 means this can be reduced as 1 minus 1 as 0 here. So, similarly if I will just put I equals to 2 here, so this will just take u3 here, and j is 1 there, then I is 2, then j plus 1 means 1 plus 1 is 2 here, minus h square f21. And if you will just put this 2 0 condition here, that is nothing but 1. So, 1, this is nothing but minus 0.02. So, this just takes the value 0.98 here, and rest of this values u11 is present, u31 is present, u22 is present there. And if you just go by fixing like since I will be vary from 1 to 3 and j is fixing there, so j equals to 1 there itself. So, further this last equation for I equals to 3, it can be written in the form of u31 to the power n plus 1, this is nothing but 1 minus omega, u31 to the power n plus omega by 4, u21 to the power n plus 1 plus u30 n plus 1 plus u41 plus u32 minus h square f31 here. If you will just see here, so this 30 value, that is nothing but 1 there itself, and this is nothing but minus 0.02. But this u41, it can be updated from this values of 31 and 21 there itself. So obviously you can just write this one as a u41 minus u21 by 2h, that is nothing but u31 here. So that's why you can just multiply the here 2h into u31, and with the multiplication of w by 4 here, so that can be taken to the left hand side, and it can be this fractional terms which will be multiplied by u31, that can be taken out to the right hand side, and it can be multiplied there itself. So that's why this u21 is repeated there. So that's why this 2 u21 to the power n plus 1 is there, u32 is there, and u41 it can be replaced in terms of u31 and u21. Similarly, if you will just vary like j equals to 2 now here, with fixing I equals to 1, 2, 3, again we can just obtain this sequence as a u12 to the power n plus 1, this equals to 1 minus omega u12 to the power n plus omega by 4, u02 plus u11 which is at n plus 1th level, u22 u13 minus h square f12. If you will just see here, so u11 to the power n plus 1, so this is already calculated here. So that's why we have just written this one as u11 to the power n plus 1 here, and 0 to n plus 1 means I equals to 0 we are just considering. So this is nothing but the fixed boundary condition, it is defined as a 1 there, and this is nothing but minus 0.02 there. Another condition, if you will just see here 1, 3, it is also known to us from the last boundary of j equals to 3, it is just defined as u equals to 1. So 1, then it is added with this one minus subtraction of this one. So that's why it is just giving 1.98 here. And u12 to the power n plus 1, it can be written in the form of minus 0.2 u12 to the power n plus 0.3 u11 to the power n plus 1 plus u22 to the power n plus 1.98. And fixing like j equals to 2, so we will just go for 2 and 3 there itself. So for this 2 point, if you will just see here, so this 3 2 and 2 3 is there. So 2 3 means this is nothing but u equals to 1, it will just take, and this is nothing but minus 0.02. So 3 2 is the unknown here, so which is known to not known to us. So this should be known from this previous cycle of calculations, and u21 this is already computed, and u12 already it is computed. So that's why we have just kept it as a u12 here, then u21 here, and u32 here, and it can be taken as 1 minus 0.202 there. And similarly, if you just go for a u32 n plus 1 here, keeping fixed 2 for I equals to 3 here, so we can just obtain this value as one boundary as here 4 2 here, and another boundary we can just find it as u33 here. So this is nothing but j equals to 3, we will have u equals to 1 minus this is 0.02, so which takes the value 0.98 here, but this u42 it can be replaced by earlier condition, that is the central difference scheme there. So it can be written as like u42 minus u of 22, this equals to like 2h into u32 there. So that's why u32 can be taken out to the left hand side, and it can be separated it. So if you just separate it out, so u22 can be repeated there itself. So that's why 2 u22 it is there, plus u31 plus 0.98 here. So if you just solve this set of equations 3 to 8 by substituting this most recent values of u, the convergence is achieved 7 iterations, which are half than those of Gauss-Seidel method. Since after 14 steps we have got this convergence solutions in a Gauss-Seidel method, but this iterated steps halved in size whenever we are just to go for this improved Gauss-Seidel method, especially called your successive or relaxation method here. So the iterative values are shown in the table, if you just see, and we are just considering these differences in each step there. And in the final step, if you are just seeing the differences here, so you can just find this order of convergence, this is going up to like 4th order here. And similarly, if you just go for this last step here, we can just obtain these differences, they are just going up to 4th order there itself also. So in each of these variables here. So with this we have just ended up this lecture. Thank you for listening this lecture.